Okay, in this video, we're going to derive the PDF for our exponential random variable. And remember, this is a continuous distribution, continuous random variable, and this is one of our key examples of continuous random variables. Okay, so the setup was we had y as the random variable that records the time until the next person enters a building. Lambda was our parameter, so it's the average number of people entering the building per unit interval, right? So we said, suppose we're in a situation where this is our unit interval. We're expecting on average, lambda people to appear, and maybe this is kind of the X indicates when, a person appears, and Y is the time until the next person enters the building. So if t equals 0 is the starting time, then Y would be however long it is until you have the first person enter the building. Now, to compute the probability, our probability density function, we first noted that we do need a PDF, not a PMF, because we have a continuous random variable. So the probability that y equals any specific value in this interval is going to be 0. Instead, it's appropriate to discuss the probability that y is in certain range, right? So we said we'll start off, for instance, if we're going from 0 to x, and x is the time when the first person appears, right? What's the probability that y is in between 0 and x? This actually is a CDF, right? Cumulative density distribution function of y. And we said we're going to compute that. So the probability that y is less than or equal to x is going to be 1 minus the probability that y is greater than or equal to x. Okay. Now, to compute the probability that y is less than or equal to x, we said the probability that y is greater than or equal to x is the same as the probability that no one appears during that first interval from 0 to x. And the fact that no one appears during the first interval, that is modeled by a brand new random variable, which is a Poisson random variable with parameter lambda times x, right? And we know, this is where we said we'll finish it in a video. So we know that probability from our formula here, right? We would let, if our parameter is now lambda times x, right, the probability, and k is equal to 0, we will have lambda x to the 0th power over 0 factorial, and then e to the minus lambda x. So we will have lambda x to the 0th power divided by 0 factorial times e to the minus lambda x. So this is the probability that the number of people that appear in this interval is equal to 0. So let's go ahead and compute this. So this is going to be 1 minus e to the negative lambda x. This is our cumulative distribution function. And now recall that the probability density function, right? So let's see here. So if f of x is the probability density function, PDF of y, then what we have is that the integral from 0 to x, say of f of t dt, is 1 minus e to the minus lambda x, right? And the notation we were using before, or on Monday, was big F. So big F is the CDF. Then this is what we've shown so far. And we said that we can use the fundamental theorem of calculus to compute f of x. It'll be the derivative of our CDF. should be the derivative of 1 minus e to the minus lambda x. And that's just going to be lambda e to the minus lambda x. So we've computed our PDF by actually deriving our CDF and then taking the derivative of it, because the derivative of CDF is going to be our PDF. Okay. So, in summary, what we'll traditionally see is if y, now typically we'll say the random variable, say has a parameter of theta, then the corresponding PDF of y is going to be 1 over theta times e to the minus x over theta. And why do we switch from the theta to the lambda? Well, it's just lambda is the average visitors per unit interval. So theta, right, is going to be the average rate, right, which is the 1 over lambda. So that's all we did was switch between the average visitors and the average rate. So I guess technically here, let's clean this up and say x exponential with average, I have it written down here, average number visitors equals lambda. Okay. So let's just finish this with some, I want to talk about, just to mention some properties of this exponential distribution. So the first property we've already mentioned, which is that our PDF is 1 over lambda, or 1 over theta, e to the minus x over theta. Notice that our f is non-negative. Remember, we said there are two key properties of a distribution. First, it's a function that's non-negative, and second, it's a function where the area under the curve is always equal to 1, right? So the integral from negative infinity to infinity, f of x dx, is going to be equal to 1. And this is good practice to double check right? You're essentially integrating, right? The second property, we're continuing with our properties here. Second property is that the expectation, and I think I've given this for homework, is going to be the theta, right? And how we compute this? Well, remember, that's the integral. And in our case, it should be from minus infinity to infinity, x, f of x, dx, where this is your PDF. And then because our PDF is 0, it'll be really, our f of x is 0. So if we want to be clear, it's 0 if x is less than 0. And this is if x is bigger than or equal to 0. Yeah? So really it's going to be from 0 to infinity. And we'll have this x. It'll be 1 over theta x e to the minus x over theta dx. And then use the change of variable, right? Or u sub. is what we call it. Use a U sub. Okay. And then the third is that the variance is going to be theta squared. And so there's a formula, right? The formula we gave for the variance is integral. It's like x minus expectation squared, and then f of x dx. So put good practice. And I think this is on the homework. Okay. And we could ask ourselves a question if, here's an example. So if students arrive at the Bayes layer according to approximately Poisson random variable with a mean rate, so we're arriving at the Bayes layer, and the mean rate is going to be 30 students per hour, and approximately Poisson random variable modeling the arrival rate. We want to know what's the probability that there's a wait time of more than 3 minutes before the next student arrives. Right? And so the solution to this would be, let's set up our random variable. So x is going to be number of students. W is going to be the waiting time between students. Right? X is going to be Poisson. What is our rate here is going to be 1/2. Because you'll have, right, if you're dealing with 30 students an hour, then you got half a student per minute. And, right, our W is going to be exponential with now a 2, right? So we're expecting 2 minutes between students. Yeah, so if you get half a student every minute, then reciprocal of that, 2 students, 2 minutes in between every student. And now, probability that W is bigger than 3 is going to be the integral from 3 to infinity. Now we need our PDF for W, and that's going to be 1/2 e to the minus W over 2 dW. Right, and you compute that. So that would give you the probability that the wait time would be more than 3 minutes for the next student. Okay. And so that wraps up our discussion of the exponential random variable. Let me know if you have questions.